In the previous lecture on harmony, I introduced this idea, this concept of transposition along a particular collection. So we talked about transposition in terms of transposition on a chromatic scale or transposition on a diatonic scale. And in this particular lecture, we'll dig deeper into this concept of transposition along a collection that turns out to be foundational for gaining a geometrical understanding on how the pitch space work in the context of many different musical traditions. And of course, here we'll focus mostly on the tonal harmony tradition of Western classical music. We can transpose along different collections and transposing along the scale or the intrinsic scale that a chord belongs to, for instance, allows us to find what is the most efficient movement between a chord and another. And this is called, in musical theory, is called voice leading or most efficient voice leading. This has to do with the way in which we actually move on a keyboard, for instance, with our fingers. So we always try to find the most efficient way of going from one chord to another, moving the least number of fingers for the least amount. So a fundamental point here is that any collection of notes, so if you talk about chords or motives or sets or scales, can be associated in principle with two different scales. One is the external scale or the enclosing scale. We can say chromatic, diatonic, or any other collection of pitches that we define as a scale. And the other one is what we call the intrinsic scale, that is the scale formed by the own notes of our collection that we start from. So in a chord settings, the notes of the chord are what an intrinsic scale is for that chord. Now, this can be represented graphically, if you want, with this kind of diagram where we move from chordal degrees in the top of this figure, and we map this onto a intrinsic scale, and then we map the scale into an actual scale, an external scale, and we can actually map the external scale eventually on the full collection of all the possible pitches. So in our 12-tone tradition, this would be the chromatic scale. Now, all the numbers that you see in these in pictures can be confusing. This is a way of actually designing an algorithm that allows you to operate at all different levels on all these different collections. And this algorithm is implemented into the Music Network library. And I'll talk briefly at the end of this lecture about the implementation. Let's talk about transposition along a collection. So transposition along the chord and transposition along the scale combine together to form kind of a parallel motion, doubly parallel motion along different nested collections. So this, again, I understand that this might be a little complex concept to explain in a short lecture like this, but I invite you also to look into supplementary materials for a fundamental textbook where I took all these ideas from, Tonality and Owner's Manual by Dimitri Timorsko, and also to follow some of Dimitri's presentations that are linked in the website. So let's kind of formalize this double transposition idea in terms of notations and operations. And here I introduce three different operators. Small case Tx, that is a transposition along the chord by a certain number of steps. And I refer here to the lecture on harmony, where I explain briefly what it means to do a transposition along a chord. Then we have a transposition along a given scale. So for instance, if I have a C major chord, C, E, G, that lives on the C major scale, C, D, E, F, G, A, B, then if I transpose along this scale, I use this operator capital Tx, where x is again the number of steps I use in the transposition. And then finally, the highest level of the hierarchy is boldface capital Tx, that is the transposition along the chromatic collection. So I can transpose my scale in the chromatic collection and then transpose the chord along the scale and create all this movement in the voice leading of my piece. Now, the useful and kind of enlightening thing to me to represent these operations graphically is the introduction of what we call the spiral diagrams. So a spiral diagram is a diagram that allows us to visualize all this transposition as a single image in a single context where everything is described graphically. So in order to construct this space, because this is a representation of the space where all these operations happen, we build what we call spirals. Spiral diagrams comes from the drawing of spirals, actually, that represent a way of combining together chords and scales so that then we can use this visualization to generate different chord progressions. The number of loops that you have in the spiral correspond to the cardinality of the chord. That means how many notes there are in a chord. If you have 2 notes, then you design a spiral with n equal 2, so n with 2 loops. If you have a triad, 3 note chords, then your spiral will have 3 loops and so on. How do we design this, or we draw this, is by start from 12 o'clock and move inwards clockwise. And then after I go for n loops, so for n number of notes in the chord loops, we stop at 9 o'clock, and from there we join the starting point. And so here you see a representation, again, in the same image here. You start from 12 o'clock, you go inward clockwise, and then you get to 9 o'clock, and then you join another loop at in order to close the 2-loop spiral. So this is the skeleton of a spiral diagram. Now we need to populate the spiral diagram with notes or chords. And so here we need to separate, distinguish between the number of notes in the chords and the number of notes in the scale. And so let's talk now about the notes in the scale. If I have k notes in the scale, what I do, I divide the circle that I generated in k slices that intercept the spiral at regular intervals. So I start again from 12 o'clock, move clockwise, and place a point every n intersection. So what I do is the following. Let's look at this particular image here on the left. What I want to do, I want to construct a spiral diagram of major triads. So I have a 3-note chord for a 7-note diatonic scale. Again, the example of the C major chord, C, E, G, 3 notes on the C major scale, 7 notes. So what I do, I start from the 12 o'clock, I draw my slices, 7 of them, and then once I've drawn them, I populate them with the different chords that I identify with the bass note. So C major would be C, the D, F, G, that would be the minor chord in the diatonic scale of C major would be D, and so on. And what I do, I start from the innermost 12 o'clock point, and then I start placing the note of the scale on each of the point in descending order. And these points are separated one from the other by the number of notes in the chord. So every 3 slices, I put a an entry, I put a note. And so let's go again to this drawing here on the left. You see I start from C, and then I start from the innermost loop. I skip the first two intersection of the sections. At the third intersection, I put my B, and then again I skip 2, and I put my A, I skip 2, and so on. I keep going until I populate the whole diagram. Now, the important thing in this kind of representation is that each point represents a complete chord. So even if I write only A or B or C in this particular diagram, each of these letters correspond to their the representing chord. So C would be C, E, G, the C major chord, and so on. And I can do this for any arbitrary number of notes in a chord, any arbitrary scale. So on the right, for instance, we have the collection of all the possible diatonic scales of 7 pitches embedded into the structure of the chromatic scale. So now we have 7 loops and 12 sections. Now, the usefulness of these kind of diagrams is that they allow us to calculate all the possible voice leading that exist within the collection of chords onto that scale. And this, again, can be done geometrically. So, for instance, we can calculate a path going from the C triad to the E triad here on a chromatic scale, and this is represented by a trajectory into this spiral. So I go, as you see here, in bold, the arrow that shows the particular trajectory that I'm following. And on the right, I have the result of this trajectory that indeed you can verify, even just by looking at it, corresponds to the most efficient voice leading, so the most efficient way of going from that chord to the next, so from C major to E major in this case. Spiral diagrams can be used to break down chord progressions, for instance. In this particular example, I'm showing here a motion between a C major chord to a B major chord, and that's like the first staff line on the right. But I can break this down following trajectories within the spiral diagram. So I can, for instance, instead of going from C to B flat, I can actually go from C to E flat to B flat and use the same this other trajectory that produces a different voice leading. And I can do this in many different ways. And so this is kind of a graphical representation of how this combination of double transpositions on the chord and along the scale give rise to particular chord progressions. This is possible because the transpositions both along the chord and along the scale should satisfy both the commutative property and the associative property, mathematically speaking. So you can actually invert the order of the operations, and you get to the same results. And using these spiral diagrams, you can build virtually any progression in the history of Western music within the tonal tradition. So this is again another representation of this spiral diagram from triads, where I would like actually to mention here that we using this the geometry of these diagrams, we can define a distance between different chords, so chords that are closer together and farther apart, and the betweenness idea, that is what I just explained, that you can factor into smaller moves larger voice leadings. Now, all this is completely generic, is not limited to any particular choice of chord, so you can start with your triads like major chords, you can use minor chords, diminished chords, cluster chords, whatever, and this is still this geometry, this operation are still valid, And so you can construct very complex harmonic spaces just by operating graphically, if you want, on these particular diagrams. So these operations and spiral diagrams are actually implemented into the music network library through a class that is called MIDI set. That is demonstrated at the end of the notebook on harmony. Although I'm not talking about that at all, so I leave you this exercise, if you wish, to try to play with all these kind of transpositions and spiral diagrams using the material in that notebook. Here you have a summary of both the attributes and the methods that are implemented into the MIDI set class. But definitely I don't think that this is a little bit more advanced than this course is supposed to be, so I leave this just to the people that are more interested and computationally minded.